Tonight, we're going to take a journey to the most dangerous, most beautiful, and most terrifying place in the entire Milky Way. Not to a distant galaxy billions of light years away, not to some theoretical place that exists only in equations. We are going to the center of our own galaxy, the place that sits 26,000 light years from where you're lying right now. A place of fire and silence, of gravity so extreme that stars move like leaves in a wind, and where a monster 4 million times the mass of our sun sits at the heart of everything we call home. By the end of tonight, you're going to understand exactly why the galactic center is the most awe-inspiring and quietly terrifying destination in the known universe, and why the atoms inside your body have a connection to that place that goes deeper than you have ever been told. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Here is the thing most people do not realize. When you look up at the night sky and see that faint smear of light we call the Milky Way, you are not looking at something distant and separate from you. You're looking inward. You're looking toward the center of the structure you live inside. Every single star you can see with your naked eye is a neighbor, a local resident of the same spiral arm you call home. But beyond them, hidden behind curtains of gas and dust so thick that no ordinary light can pass through, something waits. Something ancient. Something that has been shaping this galaxy and everything in it for over 13 billion years. And tonight, together, we are going to travel toward it. Now, let's begin. There is a place at the center of our galaxy that most people will never think about. It does not appear in the news. It does not come up in conversation. It sits there, 26,000 light years away, silent and immense, doing what it has always done, pulling, shaping, waiting. And tonight you and I are going to travel toward it together, one slow and careful step at a time. I want you to get comfortable right now. Let your body settle. Let your breathing slow. Because what we're about to explore is not something that requires urgency or tension. It requires something rarer. It requires the willingness to sit with scale, to let numbers that do not fit inside a normal human mind wash over you like water, slowly until something clicks and you feel, even for just a moment, the true size of the place you live in. The Milky Way is your home galaxy. You have known that since you were young, but knowing a fact and truly feeling it are two entirely different things. The Milky Way is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. That range alone should stop you for a moment. The uncertainty spans 300 billion suns. We cannot count them precisely. The galaxy is simply too large, too full, too ancient for us to inventory completely. It stretches roughly 100,000 light years from one edge to the other. A single light year is about 5.9 trillion miles. Multiply that by 100,000, and you begin to approach something the human brain was never designed to hold. You live on a small rocky planet orbiting a medium-sized yellow star. That star sits in a region called the Orion Arm, one of several spiral arms that curve outward from the galactic center, like the spokes of an enormous, slowly turning wheel. Your star, the Sun, is about 26,000 light years from the center of that wheel. That is the distance we are going to cover tonight. Not in a rocket. Not in any physical vessel. We are going to travel it in imagination, in language, in the quiet darkness of wherever you are right now. And I promise you, by the time we arrive, you will never look at the night sky quite the same way again. Here is something that I find quietly astonishing every time I think about it. Right now, as you lie here, the entire solar system is moving. The sun, the Earth, every planet, every moon, every asteroid in our neighborhood is orbiting the center of the Milky Way at a speed of about 514,000 miles per hour. We have been traveling at that speed for the entire history of life on Earth. And in all that time, we have completed just over 20 complete orbits of the galactic center, 20 trips around the heart of our galaxy in 4.5 billion years. One orbit takes roughly 225 million years. The last time we were in this same position in our galactic orbit, the dinosaurs had not yet appeared. And yet, despite all that motion, despite those incomprehensible speeds, the center of the galaxy feels fixed and unreachable. It is always there, always in the same direction in the sky, hidden from our eyes by enormous clouds of gas and dust that absorb visible light completely. For most of human history, we had no idea what was there. Ancient peoples looked toward the dense band of the Milky Way and saw mystery. They invented stories to explain the glow, but they could not see through it. They could not know what waited at its heart. We began to find out only in the 20th century, and what we found was more extreme, more violent, and more beautiful than anyone had imagined. It started with radio waves. In the early 1930s, a young engineer named Karl Jansky was trying to identify sources of interference in transatlantic radio communications. He built a rotating antenna, tracked down most of the noise, and then found something he could not explain. A steady hiss coming from a fixed point in the sky, a point that turned out to lie in the direction of the constellation Sagittarius, in the direction, as we would later understand, of the galactic centre. That hiss was the first whisper the centre of our galaxy ever sent us, and we almost missed it entirely. Decades of observations followed, radio telescopes, infrared cameras, X-ray satellites, each new technology peeling back another layer of the veil, and with every layer removed, the galactic centre revealed itself to be more turbulent, more crowded, and more extreme than the quiet outer galaxy we call home. Temperatures that would vaporize any known material, magnetic fields twisted into impossible shapes, stars packed so closely together that the night sky from a planet in that region would never truly be dark. It would glow, always, like permanent dawn from every direction at once, and at the very centre of all of it, something that no visible light can escape, something that bends space, stops time, and swallows everything that comes too close. We call it Sagittarius A star. It is a supermassive black hole, 4 million times the mass of our Sun, compressed into a region smaller than the distance from the Earth to the Sun. It has been there since the galaxy was young. It has been quietly governing the motion of billions of stars for billions of years. And in 2022, for the first time in human history, we took its photograph. That photograph changed something, not in the physics, not in the equations, but in the felt reality of what it means to live in this galaxy. Because seeing something, truly seeing it, even as a blurry ring of orange light against the darkness, makes it real in a way that no calculation ever quite can. The monster at the centre of our home has a face now, and tonight we are going to travel toward it, slowly, carefully, one layer of wonder at a time. I want to be honest with you about something before we go further. Parts of what we're going to explore tonight are genuinely terrifying, not in a way that should keep you from sleep, but in a way that should remind you of something important. The universe is vast beyond all reckoning, and we are very small inside it. There is a particular kind of peace that comes from truly accepting that, from letting the scale of everything dissolve the weight of the small and temporary concerns that fill our ordinary days. That is part of what tonight is for, to remind you, gently, of the size of the thing you are part of. So let yourself breathe. Let the darkness around you be not empty, but full of distance, of light travelling toward you from stars you will never visit, of gravity bending space in ways you cannot see, but are nonetheless real. You're already inside the journey. You have been your whole life. Tonight, we're simply going to pay attention to it together. Before we travel anywhere, we need to know where we're starting from. That sounds simple. But I want to take a moment with it, because most of us carry a picture of the Milky Way in our heads that is slightly wrong. Not wrong in a way that matters for daily life, but wrong in a way that matters for tonight. Because tonight, we are trying to feel the true shape of our home, and a blurry picture will not serve us well on a journey like this one. When you see images of the Milky Way from above, those sweeping photographs of a luminous spiral with long curving arms and a bright central bulge, I need to tell you something important about those images. Not a single one of them was taken from outside the galaxy. We have never sent a spacecraft far enough to look back and see the full structure. Every image you have ever seen of the Milky Way as a whole is either an artist's reconstruction, a computer model, or a photograph of a different galaxy that resembles our own. We are inside the Milky Way, and we have never left it. Everything we know about its shape we have pieced together from measurements taken from within, the way you might try to draw a map of a forest while standing inside the trees. What we have pieced together, though, is genuinely extraordinary. The Milky Way is a barred spiral galaxy. That word barred is important. At the very centre, instead of a simple round core, there is an elongated bar of stars stretching across the middle, thousands of light years long, like a straight bridge connecting two sides of the galaxy's heart. From that bar, the spiral arms curve outward, wrapping around the galaxy in great sweeping arcs. Astronomers have identified several major arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the one you live in, the Orion arm, sometimes called the Orion spur, a smaller, shorter structure branching off between two of the larger arms like a side street between two highways. Your Sun sits in the Orion arm, roughly halfway between the centre and the outer edge of the galaxy. This position, it turns out, may not be an accident. The outer regions of the galaxy are too sparse, too low in the heavy elements that planets and life require. The very inner regions, as we will discover tonight, are too violent, too densely packed, too flooded with radiation for complex chemistry to survive easily. The middle zone, where you are, is sometimes called the galactic habitable zone, a band of relative calm and chemical richness, where the conditions for life are at least not immediately hostile. You were born in the one neighbourhood of a 400 billion star city where the schools are decent and the radiation levels are not instantly lethal. That is either extraordinary luck, or it tells us something deep about the conditions life requires. Perhaps both. Now close your eyes for a moment and try to picture the disk of the galaxy from the side. It is not perfectly flat. It has a slight warp, like a vinyl record left too long in the sun, curving gently upward in some regions and downward in others. The disk itself is relatively thin compared to its width. If the galaxy were the size of a dinner plate, the disk would be roughly as thick as a sheet of paper. Most of the stars, most of the gas, most of the ongoing star formation happens within that thin layer. But above and below the disk, surrounding the entire structure like a faint ghostly halo, is a vast sphere of older stars, ancient globular clusters, and enormous quantities of invisible matter we can detect only through its gravitational effects. We call that invisible component dark matter, and it outweighs all the visible stars and gas in the galaxy by a factor of roughly 5 to 1. The galaxy you live in is mostly made of something we cannot see and do not yet fully understand. The galactic centre lies in the direction of the constellation Sagittarius. If you're ever outside on a clear summer night in the northern hemisphere, and you look toward the south, toward that dense and milky band of a light crossing the sky, you are looking toward the centre of the galaxy. The light you see in that band represents billions of stars, most of them too faint and too distant to resolve individually, blending into a soft, continuous glow. But the actual centre, the true heart of it all, is hidden behind roughly 26,000 light-years of intervening material. Dust clouds so thick and so vast that they absorb nearly all the visible light trying to pass through them. For most of human history, that dust was an impenetrable curtain. The centre of the galaxy was a rumour, an inference, a direction with a mystery at the end of it. To truly understand what that distance means, I want to give you an analogy. Light travels at about 186,000 miles per second. In 1 year, it covers roughly 5.9 trillion miles. The centre of the Milky Way is 26,000 of those years away at that speed. If you sent a light signal toward the galactic centre tonight, it would arrive there in the year 28,026. Every civilization that has ever risen and fallen on this planet, every empire, every language, every invention from the first stone tool to the device you are using right now, all of that human story fits inside a span of time that is a fraction of the time it would take your message to arrive. And that is just the distance to the centre of our own galaxy, not to the edge of the observable universe, not to a neighbouring galaxy, just to the middle of our home. And yet, in another sense, the galactic centre is not remote at all. Everything in this galaxy is in motion, orbiting around that central point. You are in orbit around it right now, as you lie here in the dark. The matter that makes up your body, the carbon, the oxygen, the iron in your blood, was forged in stars that themselves orbited the galactic centre billions of years before the Sun existed. Those stars lived, burned, exploded, and scattered their material outward across the galaxy. That material drifted, clumped, condensed, and eventually became the solar nebula from which the Sun, the Earth, and you were made. Your atoms have already made the journey to and from the inner galaxy, in a sense. They were born closer to the centre than you are now and travelled outward over billions of years to become part of you. There is something quietly moving about that thought. We tend to think of the galactic centre as somewhere else, somewhere foreign and unreachable. But the connection is real and physical. You're not a visitor to this galaxy looking at the centre from a safe distance. You're a product of the galaxy's long history, built from material that has been cycling through its stars and clouds and arms for most of the universe's existence. The centre is not separate from you. It is, in some deep and literal sense, where part of you comes from. As we begin to move inward tonight, I want you to hold that thought. The journey we're taking is not just outward into the unknown. It is also, in a strange and beautiful way, a journey back towards something ancient and familiar. The galaxy's centre shaped the stars that made your atoms. And now, for the first time in that entire long story, one of those atoms has become aware enough to turn around and look back toward the place it came from. That seems worth paying attention to. That seems worth the journey. Most people, when they think about space, think about emptiness. They picture the vast stretches between stars as pure void, a perfect vacuum, and nothing so complete that it borders on the abstract. And in one sense, that picture is not wrong. Space is extraordinarily empty by any standard a human being can relate to. But in another sense, and this is the thing most people do not realize, the space between the stars is not empty at all. It is filled, thinly, unevenly, sometimes almost imperceptibly, but genuinely filled, with gas and dust and magnetic fields and ancient light and particles streaming outward from distant suns. The road between the stars is not a void, it is a landscape. And tonight, as we begin our journey inward toward the galactic centre, we're going to travel through it. Astronomers call this material the interstellar medium. That phrase, interstellar medium, sounds dry and technical, but the reality it describes is one of the most varied and beautiful environments in the known universe. The interstellar medium is not uniform. It comes in phases, in layers, in wildly different densities and temperatures depending on where you are and what has happened nearby. In some regions, it is a scalding hot plasma, heated to temperatures of millions of degrees by the shockwaves from ancient stellar explosions, so thin that it barely qualifies as matter by earthly standards, but so energetic that it glows in X-rays. In other regions, it is a warm, diffuse gas of neutral hydrogen, drifting slowly in the spaces between star systems, cool and quiet, invisible to the naked eye but detectable by radio telescopes tuned to just the right frequency. And in still other regions, the coldest and densest of all, it collapses into clouds so thick with molecules that stars are born inside them. As we leave the neighbourhood of the Sun and begin travelling inward, one of the first things we encounter is the structure of these clouds. Our immediate galactic neighbourhood is relatively clear. The Sun sits inside what astronomers call the local bubble, a region of unusually hot and thin gas stretching several hundred light-years in most directions. This bubble was carved out over millions of years by a series of supernova explosions from massive stars that lived and died in this part of the galaxy before the Sun was born. The blast waves from those explosions swept the surrounding gas outward, leaving behind a cavity of hot, tenuous plasma. We have been travelling through that cavity for a very long time, and in cosmic terms it is a relatively comfortable neighbourhood. What lies beyond it is denser, more complex, and far more interesting. As we move deeper into the galaxy, the density of the interstellar medium begins to rise. We pass through spiral arm after spiral arm, each one a region where gas and stars and dust are compressed slightly more than average by the gentle gravitational waves that give the galaxy its spiral shape. In the arms, star formation is actively underway. Enormous clouds of molecular hydrogen, cold and dark and containing millions of times the mass of the Sun, are slowly collapsing under their own gravity. Deep inside those clouds, invisible from the outside, new stars are igniting for the first time. These molecular clouds are among the largest coherent structures in the galaxy. Some of them span hundreds of light years. From within one, you would have no sense of its scale, surrounded on all sides by dark, cold gas, unable to see more than a tiny fraction of the structure you were inside. The dust mixed into these clouds is worth pausing on, because it plays a role that goes far beyond mere obscuration. Interstellar dust grains are tiny, most of them smaller than the particles in cigarette smoke, but they are chemically complex. They are coated in ices made of water, methanol, ammonia, and carbon dioxide. On their surfaces, chemical reactions occur that would not be possible in open space. Simple molecules combine into more complex ones. Some of the basic organic chemistry that eventually leads to the building blocks of life takes place on the surfaces of these cold, drifting grains, trillions of miles from any star in the dark interior of molecular clouds. The emptiness between the stars is, in a quiet and unannounced way, a chemistry laboratory. It has been running experiments for billions of years. One of the most striking things about travelling through the interstellar medium is the light, or rather, the absence of it. Out here between the stars, beyond the warm glow of any individual sun, the darkness is almost total. If you could somehow survive in interstellar space and look around you, the stars would be brilliant points against an otherwise perfect black. There would be no diffuse glow, no scattered light, no sense of ambient illumination the way there is on Earth, even on a cloudy night. Just hard, sharp stars set into absolute darkness, and the occasional faint shimmer of a nearby nebula or cloud lit from within by the infant stars being born inside it. It is a darkness that is difficult to imagine from a planet perpetually bathed in reflected and scattered sunlight, clean darkness, ancient darkness, the darkness that existed before any star was born. As we push further inward, past the halfway point of our journey, the sky around us begins to change in a way that is subtle at first, and then impossible to ignore. The stars become more frequent, not dramatically, not all at once, but steadily. The number of stars visible in every direction increases. We are moving into the inner galaxy, where stellar density is higher, where the spiral arms are more tightly wound, where the history of star formation goes back further, and the population of stars is older and more varied. Ancient red giants drift alongside younger blue-white stars. Globular clusters, tight spherical swarms of hundreds of thousands of old stars bound together by gravity, hang in the darkness like luminous cities seen from a great distance. And woven through all of it, threading between the stars and around the clouds and through the arms, are magnetic fields. The interstellar medium is permeated by magnetic fields on scales that stretch for thousands of light years. These fields are not strong by the standards of a laboratory magnet or even the Earth's own magnetic field, but they are vast, and they play a role in governing the behaviour of the charged particles drifting through interstellar space, shaping the flow of cosmic rays, influencing the way clouds collapse to form stars, threading structure into what might otherwise seem like formless gas. The space between the stars is not passive, it is active, dynamic, threaded with invisible forces that connect distant regions of the galaxy to one another in ways we are still working to fully understand. By the time we reach the inner few thousand light-years of the galaxy, the interstellar medium has transformed almost beyond recognition compared to what we left behind near the Sun. The gas is hotter, denser, and more turbulent. The magnetic fields are stronger and more tangled. The rate of star formation is higher, and the deaths of massive stars exploding as supernovae pump enormous energy into the surrounding medium, driving shockwaves that compress and heat the gas, triggering new rounds of star formation in a violent and self-reinforcing cycle. The road has brought us somewhere fundamentally different. The quiet interstellar highways of the outer galaxy have given way to something far more intense. We are approaching the inner regions now, and the landscape is beginning to reflect the proximity of the thing that rules this entire structure. The centre is getting closer, and everything around us is starting to show it. Imagine standing outside on the clearest night you have ever experienced. No moon, no city lights, no clouds, just you and the full depth of the sky above you. On a night like that, from a dark location on Earth, you can see roughly 5,000 stars with your naked eye. 5,000 points of light scattered across the dome of the sky, some bright and sharp, some faint and trembling at the edge of visibility. It feels like a lot. It feels, in fact, like an overwhelming abundance of stars, more than you could ever count or name. Now imagine that same sky, but with every single one of those stars replaced by something 100 times brighter. And then imagine 10,000 more added on top of those, and then 10,000 more. That is beginning to approach what the night sky looks like as you travel into the inner regions of the Milky Way, where the stars are no longer scattered like distant lanterns but packed together like a crowd, shoulder to shoulder, blazing from every direction at once. The stellar density in the outer galaxy, in the neighbourhood where our Sun lives, is relatively modest. Stars in our region are separated by distances averaging roughly a few light years. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. That is about 25 trillion miles of empty space between us and our closest neighbour. In the outer galaxy, this kind of spacing is normal. Stars are islands, isolated from one another by vast seas of nothing, each one burning alone in its own private darkness. But as you move inward toward the galactic centre, that isolation begins to dissolve. The average distance between stars shrinks, first to 1 light year, then to fractions of a light year. Deep in the central bulge of the galaxy, stars are separated by distances measured in light weeks, or even light days rather than light years. They are not touching, not colliding in most cases, but they are crowded together in a way that has no parallel anywhere in the outer galaxy. This crowding has consequences that go far beyond the visual spectacle, though the visual spectacle alone is staggering. On a hypothetical planet orbiting a star deep in the inner galaxy, night would not look anything like the night you know. The sky would not be dark. It could not be dark. With stars so close and so numerous in every direction, the combined light of the nearest thousands of stellar neighbours would fill the sky with a permanent diffuse glow, not the sharp brilliance of a daylit sky, but something softer and more unsettling, a never-ending twilight, a sky that never truly went black, that never offered the full darkness that living creatures on Earth have always been able to find by simply waiting for the sun to set. The concept of a truly dark night, the kind of night you might be lying in right now, would be unknown on such a world. There would always be light, always a glow, always the reminder, visible in every direction, that you are deep inside one of the most densely populated regions of a 400 billion star galaxy. The stars themselves in this inner region are not the same as the ones we know in our neighbourhood. The inner galaxy is home to a disproportionate number of old stars, ancient red giants and yellow giants that have been burning for 10 or 12 billion years, carrying within them the chemical history of the galaxy's earliest epochs. But it is also home to something that surprised astronomers when they first discovered it: regions of intense, ongoing star formation, producing some of the most massive and luminous stars that exist anywhere in the Milky Way. These are not ordinary stars. These are objects so extreme in their properties that they push against the theoretical upper limits of what a star can be. Stars containing 50, 80, even 150 times the mass of our Sun. Stars that burn so hot and so bright that they exhaust their fuel, not in billions of years, but in millions. Brief, violent, catastrophic lives measured in cosmic eye blinks, ending in explosions that for a moment outshine entire galaxies. One of the things that makes the inner galaxy so extraordinary is the sheer variety of stellar populations, packed into a relatively small volume of space. You have ancient stars, billions of years old, drifting on slow orbits that predate the formation of the solar system by almost twice its entire age. You have young, ferociously hot stars that formed within the last few million years, still embedded in the remnants of the gas clouds that gave birth to them. You have dying stars, red giants swollen to hundreds of times their original size, shedding their outer layers into space in slow, luminous winds. You have stellar corpses, neutron stars and white dwarfs, the dense remnants of stars that already lived their full lives and collapsed. All of these populations coexist in the inner galaxy, layered on top of one another in a complex living archive of the galaxy's entire history. Walking through the inner galaxy would be like walking through a library where books from every era of human civilization are stacked together on the same shelves, the newest pages pressed against the oldest. The gravitational environment in this crowded inner region is also fundamentally different from what we experience in the outer galaxy. In our neighbourhood, the gravitational influence of neighbouring stars is negligible on any human timescale. Proxima Centauri's gravity does not meaningfully affect the motion of our solar system, but in the inner galaxy, where stars are much closer together, gravitational interactions between neighbouring stars are far more frequent and far more significant. Over millions of years, stars in the inner galaxy can have their orbits perturbed, their trajectories shifted, their planetary systems disrupted by close encounters with other stars. Any planets orbiting stars in the inner galaxy face a far more chaotic gravitational environment than Earth does. The stability that allowed life on Earth to persist and evolve over billions of years, undisturbed by stellar neighbours, is much harder to maintain in a region where the neighbours are so close and so numerous. There is also the question of radiation. Massive luminous stars pour out enormous quantities of ultraviolet radiation and energetic particles. In a region crowded with such stars, the radiation environment is intense. Supernovae, the explosions of massive stars at the end of their lives, are far more frequent in the star-forming regions of the inner galaxy than they are in our quiet outer arm. Each supernova sends a shockwave of energy and particles expanding outward through the surrounding gas, heating it, compressing it, and flooding nearby space with high-energy cosmic rays. A planet in the inner galaxy would be bathed in levels of ionizing radiation that would present serious challenges for the development and persistence of complex chemistry on its surface. And yet, despite all of this, the sheer spectacle of the inner galaxy is something that demands a kind of reverence. Those blazing skies, those ancient and enormous stars drifting on orbits that have not changed since before the Earth existed, that permanent twilight glow from 1,000 neighbouring suns, there is a terrifying beauty to it, a beauty that is inseparable from its violence, the way a storm at sea is beautiful precisely because of its power. We are still far from the centre. We have not yet encountered the true extremes that wait for us deeper in. But already the galaxy around us has become something unrecognisable from the quiet, dark, star-scattered sky of home. We are inside something vast and blazing now, and it is only going to intensify from here. There is a moment on any long journey when the landscape changes so completely that you know, without being told, that you have crossed into somewhere fundamentally different. The air feels different. The light is different. The rules seem subtly altered. On our journey toward the heart of the Milky Way, that moment arrives when we enter what astronomers call the central molecular zone. We are now within the innermost 1,000 light-years of the galaxy, and everything, quite literally everything, is different here. The central molecular zone is a region that defies easy description, because it defies almost every expectation built up by studying the rest of the galaxy. It is a ring, or more precisely a collection of dense molecular clouds arranged in a roughly ring-like structure around the galactic centre, containing somewhere between 50 million and 100 million times the mass of our Sun in gas and dust alone. That is an almost incomprehensible quantity of raw material. But what makes the central molecular zone truly strange is not its mass. It is its behaviour. The gas here does not follow the same rules as the gas in the outer galaxy. It is hotter than it should be. It is more turbulent than it should be. And it is threaded through with magnetic fields far stronger than anything found in the quiet spiral arms where our Sun lives. In the outer galaxy, molecular clouds are cold, deeply, profoundly cold. We are talking about temperatures of around 10 degrees above absolute zero, roughly minus 263 degrees Celsius. At those temperatures, chemistry slows almost to a standstill, molecules drift in frozen suspension, and the clouds sit quietly for millions of years before gravity eventually coaxes them into collapsing and forming stars. The central molecular zone breaks this pattern entirely. The molecular gas here has temperatures ranging from several tens of degrees above absolute zero to, in some regions, hundreds of degrees above absolute zero. That might still sound cold by human standards, but for a molecular cloud it is extraordinarily warm. Something is heating this gas, pumping energy into it continuously, keeping it in a state of turbulent agitation that the cold outer galaxy never experiences. What that energy source is, and in what proportions different mechanisms contribute to it, is still one of the active and unresolved questions of galactic astronomy. The turbulence is equally striking. Gas clouds in the outer galaxy move slowly and gently relative to one another, drifting on the long, patient timescales of galactic rotation. In the central molecular zone, the gas moves with a violence that seems almost incompatible with the formation of stable structures. Clouds collide, shockwaves ripple through the medium, streams of gas twist and shear against one another in motions driven partly by the intense gravitational field of the galactic centre, and partly by the energy released by the dense population of massive stars being born and dying in this region. The central molecular zone is not a quiet nursery for stars. It is a turbulent, churning environment where the processes of birth and destruction overlap and interweave in ways that have no equivalent anywhere else in the galaxy we can easily study. One of the most famous structures within the central molecular zone is a cloud known as Sagittarius B2, or SCRA B2 for short. It is one of the largest and most massive molecular clouds in the entire Milky Way, located about 120 light-years from the galactic center. Sagittarius B2 contains around 10 million times the mass of the Sun in gas alone, and it is one of the most active star-forming regions anywhere in the galaxy. But it is also famous for something that sounds almost whimsical when you first hear it. It contains enormous quantities of complex organic molecules: methanol, ethanol, formic acid, glycolaldehyde, which is a simple sugar, aminoacetonitrile, a precursor to the amino acid glycine. The molecular richness of Sagittarius B2 is astonishing, a reminder that the chemistry of life is not confined to the surfaces of planets, but is scattered across the interstellar medium in quantities that dwarf anything found in any individual solar system. The magnetic fields threading through the central molecular zone are in a class of their own. In our part of the galaxy, the interstellar magnetic field is relatively weak and follows the broad spiral structure of the disk, running roughly parallel to the galactic plane. In the central molecular zone, the magnetic field is far stronger and, in many places, runs perpendicular to the galactic plane, pointing straight up and down out of the disk rather than along it. This perpendicular orientation creates one of the central molecular zone's most visually dramatic features when observed in radio wavelengths: long, thin, parallel threads of radio emission stretching vertically for hundreds of light-years, like the strings of an enormous and invisible instrument. These filaments, discovered in the 1980s, are still not completely understood. They appear to trace the paths of high-energy electrons spiraling along magnetic field lines, but the origin of those electrons and the processes that create such sharply defined, geometrically regular structures in what is otherwise a turbulent and chaotic environment remain subjects of active research and occasional genuine disagreement among astronomers. The star formation happening within the central molecular zone is not simply more of what happens in the outer galaxy, it is qualitatively different. In the outer galaxy, the conditions for star formation are relatively well understood. A cloud becomes dense enough, gravity overcomes the thermal and magnetic pressure supporting it, and it collapses. In the central molecular zone, the high turbulence and strong magnetic fields should, by normal calculations, prevent most of the gas from collapsing at all. The clouds should be too agitated, too magnetically supported, too violently stirred to settle down and form stars, and yet they do form stars, at a rate comparable to, or even exceeding what you would expect from clouds of similar mass in the outer galaxy. Something is overcoming the turbulence. Something is driving collapse despite the conditions that should prevent it. This discrepancy between theory and observation is one of the genuinely open puzzles of modern astrophysics, a place where our models of star formation break down and have to be rethought. As we move through this zone, the sense of being in an extreme and alien environment becomes impossible to ignore. The sky is filled with radio emission, with infrared glow, with the hard blue light of young, massive stars burning brilliantly for their brief lives before exploding. The gas around us is warm, dense, and turbulent, nothing like the cold, quiet clouds of the outer galaxy. The magnetic fields are strong enough to structurally influence the flow of material on scales of hundreds of light-years. And deeper in, closer to the center still, the conditions are only going to become more extreme. We have crossed a threshold. The central molecular zone is the antechamber to the most dramatic region of the galaxy, and it is already more alien than most of the universe we have traveled through to get here. The center is close now. We can feel it in the temperature of the gas, in the violence of the turbulence, in the intensity of everything pressing against us from every direction. Something enormous waits just ahead, and the material around us is responding to its presence the way iron filings respond to a magnet, oriented, agitated, drawn irresistibly toward the thing at the heart of it all. There is a particular kind of awe that comes not from encountering something vast and distant, but from encountering something that should not exist. Something that sits at the very edge of what the laws of physics permit, that pushes against theoretical limits so hard that scientists, when they first discovered it, genuinely questioned whether their instruments were malfunctioning. That is the feeling that comes with learning about two star clusters that sit within the innermost 100 light-years of the Milky Way. two clusters that are, by almost any measure, the most extreme collections of stars anywhere in our galaxy. We call them the Arches cluster and the quintuplet cluster, and they are, in the most precise sense of the word, monstrous. Let me first give you a sense of what a normal star cluster looks like, so you can appreciate how far beyond normal these two structures sit. In the outer galaxy, open star clusters are common. The Pleiades, that familiar tight grouping of blue-white stars visible on winter nights, is a typical example. It contains somewhere around 1,000 stars spread across a region roughly 40 light-years across. Its most massive stars are perhaps 10 times the mass of the Sun. It is young by stellar standards, only about 100 million years old, and its stars are gradually drifting apart as gravitational interactions slowly unbind the cluster over millions of years. It is beautiful, it is interesting, and by the standards of the galactic center, it is utterly unremarkable. A quiet village compared to what waits near the heart of the galaxy. The Arches cluster sits approximately 100 light-years from Sagittarius A star, the supermassive black hole at the galactic center. It is the densest known star cluster in the entire Milky Way. Within its core, roughly 1.5 light-years across, there are more than 100 massive stars crammed into a volume of space that, in our neighborhood, might contain no stars at all. The total mass of the Arches cluster is estimated at around 10,000 solar masses, concentrated into a region so compact that the stars near its center are separated by distances less than 1/10 of a light-year. If our Sun were located in the core of the Arches cluster, instead of in the quiet outer galaxy, the 10 nearest stars would all be within a few weeks of travel time at the speed of light. The night sky would be unrecognizable. Brilliant blue-white giants blazing in every direction, close enough that several of them would be comparable in apparent brightness to a full moon. But the true extremity of the Arches cluster is not its density. It is the nature of its stars. The cluster contains more than 150 stars with masses exceeding 20 times that of our Sun. Several of its most massive members approach, or exceed 100 solar masses. These are among the most luminous stars known anywhere in the Milky Way, burning so intensely that they radiate more energy in a single second than our Sun radiates in several weeks. They are so hot that the surface temperature of the hottest among them exceeds 50,000 degrees, compared to our Sun's relatively modest 6,000 degrees. They are classified as Wolf-Rayet stars and O-type supergiants, categories that represent the absolute extreme end of the stellar mass spectrum. Stars that live fast, burn furiously and die young, exploding as supernovae after lifetimes of just a few million years. The Arches cluster itself is only about 2 million years old. In stellar terms, it is a newborn. Its most massive stars have not yet had time to reach the end of their lives, which means we are seeing it at its peak luminosity, at the most spectacular moment of its brief existence. In another few million years, those massive stars will begin to explode one after another, each supernova pumping energy into the surrounding gas and gradually unbinding the cluster from within. The dense, blazing structure we observe today will dissolve. Its stars will scatter into the broader stellar population of the inner galaxy, carrying with them the heavy elements forged in their cores. What looks today like a permanent and overwhelming feature of the galactic center is, on cosmic timescales, a temporary and fleeting phenomenon. A firework caught at the moment of its greatest brightness. The quintuplet cluster, located roughly 30 light-years from the Arches cluster and about 100 light-years from the galactic center, is slightly older at around 4 million years, and it tells a story about what happens next. Its most massive stars have already evolved off the main sequence and are now in spectacular and unstable late stages of their lives. The cluster takes its name from 5 extremely luminous stars that were among the first identified within it, but its full population is far larger, containing hundreds of massive stars in various stages of their dramatic evolution. Some of its most luminous members are luminous blue variable stars, objects so massive and so energetic that they are barely stable, periodically erupting in outbursts that shed entire solar masses of material into space in a matter of years. The Pistol star, one of the most luminous stars known in the Milky Way, was long believed to be a member of the quintuplet cluster. Its luminosity is estimated at around 1.5 million times that of our Sun. A single star in a single cluster near the center of our galaxy, outshining the entire combined output of 1.5 million suns. What does it mean that these clusters exist so close to the galactic centre? It means that the environment near Sagittarius A star is not simply hostile to star formation, it is capable of producing the most extreme star formation events in the entire galaxy. The tidal forces near the galactic centre are enormous, strong enough to shear apart most molecular clouds before they can collapse. The turbulence, as we explored in the previous stretch of our journey, should suppress star formation, and yet here are two of the most massive and luminous star clusters anywhere in the Milky Way, sitting within 100 light-years of the supermassive black hole, formed within the last few million years. The galactic centre is not only not hostile to star formation in all circumstances, it is apparently capable, under the right conditions, of producing stellar nurseries that dwarf almost anything found anywhere else. How this happens, how gas manages to collapse and form stars in such an extreme tidal environment, is another of the genuinely open and actively debated questions at the frontier of galactic astrophysics. There is something almost paradoxical about these clusters that I find deeply compelling when I sit with it in the quiet. The most violent, most extreme, most physically hostile region of our galaxy is also the site of the most spectacular stellar birth events our galaxy currently hosts. Creation and destruction, operating simultaneously and inseparably, at scales and intensities that make the processes of the outer galaxy look gentle by comparison. The Arches cluster and the quintuplet cluster are not anomalies on the edge of what the galactic centre does. They are expressions of its character, concentrated, blinding evidence that the heart of our galaxy is not merely large and old and dark. It is alive, it is burning, and it is making new stars in conditions that should make star formation impossible. The centre of the Milky Way does not follow the rules we wrote for the outer galaxy, it writes its own. And we are almost close enough now to begin to feel the full weight of that fact. One of the most humbling things about modern astronomy is how much of the universe is invisible to us in ordinary light. The universe we see with our eyes, the stars and planets, and the soft glow of the Milky Way on a clear night, is only one thin slice of the full electromagnetic spectrum. Below visible light there are radio waves, microwaves, and infrared radiation. Above it there are ultraviolet light, X-rays and gamma rays. Each of these wavelengths reveals a different layer of reality, a different set of processes and structures that are completely invisible to the others. And nowhere is this more dramatically true than at the galactic centre, where some of the most extraordinary structures in the entire Milky Way exist, in forms that human eyes, unaided by technology, would never detect at all. To see the galactic centre as it truly is, you have to learn to look with instruments tuned to frequencies far beyond the rainbow. And when you do, what appears is genuinely shocking. Let us begin with the magnetic filaments, because they were among the first truly anomalous structures discovered at the galactic centre, and because they remain, decades after their discovery, not fully explained. In the early 1980s, astronomers using radio telescopes began to notice something strange in the region around Sagittarius A star. Thin, bright threads of radio emission, extraordinarily narrow and extraordinarily long, running perpendicular to the galactic plane. Not horizontal, following the flat disk of the galaxy the way most structures do, but vertical, stabbing straight up and down out of the plane like needles thrust through a sheet of paper. These filaments, now known collectively as non-thermal radio filaments, are typically a few light-years wide but can stretch for 50, 100, or even 300 light-years in length. They're almost perfectly straight. They run parallel to one another with a geometric regularity that seems, at first glance, almost artificial, almost designed. The leading explanation for these filaments involves the strong magnetic fields of the central molecular zone, those perpendicular fields we encountered earlier that run vertically through the inner galaxy. The filaments appear to trace bundles of magnetic field lines, illuminated by high-energy electrons spiraling along those lines and emitting radio waves as they do so. Think of them as the magnetic skeleton of the galactic centre, made briefly visible, lit up from within by energetic particles rushing along the invisible corridors of the field. The electrons responsible for this emission are moving at very close to the speed of light. Where do they come from? That question is less settled. Some may come from supernova remnants nearby. Some may be accelerated by the complex magnetohydrodynamic processes operating in the turbulent gas of the central molecular zone. Some possibly are connected to activity from Sagittarius A star itself. The honest answer is that we are still working it out, and the filaments remain one of the most intriguing unsolved puzzles in the study of the galactic centre. Beyond the filaments, the galactic centre reveals another extraordinary feature when observed in X-rays and radio waves: enormous lobes of hot plasma extending above and below the galactic plane. These are not small structures. They are not local phenomena confined to the immediate neighbourhood of the black hole. The lobes of hot gas associated with the inner galactic centre stretch for hundreds of light years perpendicular to the disk, filling the space above and below the central molecular zone with plasma heated to temperatures of tens of millions of degrees. The energy required to inflate and maintain these lobes is staggering, far beyond what ordinary stellar winds or supernova explosions in the region could plausibly provide on their own. Something more powerful has been at work here, something that can inject energy into the surrounding medium at rates that make the output of entire star clusters look modest by comparison. Part of the answer almost certainly involves the collective effect of the intense star formation in the inner galaxy. When thousands of massive stars form in a small region of space over a geologically short period of time, the combined effect of their stellar winds and eventual supernova explosions can drive what astronomers call a starburst-driven outflow, a superwind of hot gas blown out of the galactic plane by the sheer pressure of all that energy deposited in a small volume. The galactic centre has undergone multiple episodes of intense star formation over its history, each one potentially driving pulses of hot gas upward and outward into the halo above and below the disk. The lobes we observe today may be the accumulated result of millions of years of such activity, layer upon layer of ejected material piling up into structures of truly galactic scale. But there is another contributor that cannot be ignored, and it connects directly to the thing waiting at the very centre of all of this. Sagittarius A star, the supermassive black hole, is today relatively quiet. It accretes gas at a low rate and produces relatively little energy compared to the active galactic nuclei seen in other galaxies. But the evidence increasingly suggests that it was not always so restrained. There are X-ray light echoes, fluorescent signals from molecular clouds near the galactic centre that appear to be responding to a burst of high-energy radiation that originated from the direction of Sagittarius A star somewhere between 100 and a few hundred years ago. The clouds are glowing not from their own energy, but from reflected light, X-ray light, from an event that happened near the black hole in what is, by cosmic standards, the very recent past. Sagittarius A star burped not long ago, and the gas clouds around it are still lit up from the flash. This recent minor activity is a whisper compared to what the Fermi bubbles, which we will explore later in our journey, suggest about the more distant past. But it is enough to remind us that even a quiet black hole is not truly inert. It flickers. It occasionally swallows a cloud of gas or a disrupted star and briefly brightens before settling back into its current subdued state. Each of those events injects energy into the surrounding medium. Over millions of years, even relatively modest and intermittent activity from a 4 million solar mass black hole adds up to an enormous cumulative energy input. The plasma lobes and their embedded magnetic filaments are, in this reading, a kind of cumulative diary of the galactic centre's history, written not in words but in the distribution of hot gas and glowing magnetic threads across hundreds of light years of space. What I find most striking about all of this, as we continue our journey inward, is the interconnectedness of everything we are seeing. The magnetic filaments are lit by energetic electrons, whose origin connects to supernovae that connect to massive star formation that connects to the turbulent gas dynamics of the central molecular zone that connects, ultimately, to the gravitational influence of Sagittarius A star organizing everything around it. The plasma lobes are shaped by stellar winds and supernova explosions, and by episodic activity from the black hole, all of it woven together into a single, complex, evolving system. The galactic centre is not a collection of separate phenomena sitting next to one another. It is one thing, an intricate, violent, ancient and still active engine, and every structure we encounter on our approach is a part of its machinery. We are inside the engine now, moving toward its core, and the structures around us are getting stranger, more extreme, and more directly connected to the thing at the very centre with every step we take. We have arrived, after travelling through the interstellar medium, through the blazing inner galaxy, through the turbulent central molecular zone, past the monster star clusters, and the impossible magnetic filaments and the lobes of scalding plasma, we are here. We are at the centre of the Milky Way, and what sits here, at the precise gravitational heart of everything we call our home galaxy, is something that belongs to a category of objects so extreme that for decades after its theoretical prediction, many serious scientists doubted it could actually exist. A black hole, not a small one, not the kind that forms when a single massive star collapses at the end of its life. Something incomparably larger, something that has been here since the galaxy was young, growing slowly and patiently over billions of years, feeding on gas and stars and everything that has ever wandered too close. We call it Sagittarius A star, and it is 4 million times the mass of our Sun. Let me try to give you a sense of what that number means, because 4 million solar masses is the kind of figure that the mind accepts intellectually and then quietly refuses to feel. Our Sun is itself an almost incomprehensibly large object. Its diameter is about 109 times that of Earth. More than 1 million Earths could fit inside it. It contains 99.8% of all the mass in the entire solar system. Jupiter, Saturn, and every other planet combined make up most of the remaining fraction. The Sun is, by any human standard, enormous. Now take 4 million of them, compress all of that mass into a single point, or rather, into a region so small that even describing its size requires concepts that strain ordinary language. The event horizon of Sagittarius A star, the boundary beyond which nothing, not matter, not light, not any signal of any kind can escape, has a radius of about 12 million kilometers. That sounds large until you realize it means the event horizon would fit comfortably inside the orbit of Mercury. The nearest planet to our Sun orbits at a distance of roughly 58 million kilometers. The most massive object in our galaxy, 4 million times the mass of the Sun, has an event horizon smaller than Mercury's orbit. Gravity compressed 4 million suns into a space that, on the scale of the solar system, is almost modest. The concept of a black hole is one that most people have encountered in some form. But I want to take a moment with what it actually means, in physical terms, to stand at the edge of one. A black hole is a region of space where the escape velocity, the speed you would need to reach in order to escape the gravitational pull, exceeds the speed of light. Escape velocity is a concept you can relate to from everyday experience. On Earth, the escape velocity is about 11 kilometers per second. That is the minimum speed a rocket needs to achieve to leave Earth's gravity without falling back. On the Moon, which is smaller and less massive, the escape velocity is lower. On Jupiter, which is larger and more massive, it is higher. On a neutron star, the incredibly dense remnant of a collapsed massive star, the escape velocity approaches a significant fraction of the speed of light. And on a black hole, the escape velocity at and below the event horizon reaches and exceeds the speed of light itself. Since nothing in the universe can travel faster than light, nothing inside the event horizon can ever escape. Not matter, not radiation, not information, not time as we normally experience it. The event horizon is the universe's most absolute one-way door. Sagittarius A star was not always known to us. Its existence was inferred long before it was directly observed. In the 1970s, two radio astronomers named Bruce Ballack and Robert Brown were mapping radio emissions from the centre of the Milky Way when they identified an extremely compact and unusually bright radio source sitting right at the dynamical centre of the galaxy. It was unlike anything else in the map, too small, too bright, too perfectly positioned to be a chance alignment. They named it Sagittarius A star, the asterisk in the name a convention, indicating it was the most notable component of a larger radio complex in that region. For years it remained a radio source, an anomaly, a thing inferred from indirect evidence. The question of what it actually was, whether it truly harboured a black hole, could not be answered by radio observations alone. The answer came through decades of painstaking observation of the stars surrounding it. Beginning in the 1990s, two independent teams of astronomers, one led by Reinhard Genzel in Germany and one led by Andrea Ghez in the United States, began using infrared telescopes equipped with adaptive optic systems to peer through the dust obscuring the galactic centre and track the motions of individual stars in the immediate vicinity of Sagittarius A star. What they found over the following years was extraordinary. The stars near the centre were not drifting lazily on long, slow orbits, the way stars in the outer galaxy do. They were moving fast, terrifyingly fast. Some of them were completing full orbits in just decades, tracing tight ellipses around an invisible central point with speeds reaching several % of the speed of light at closest approach. The only thing that could explain those orbits, the only mass compact enough to be invisible, and yet powerful enough to whip stars around like that, was a supermassive black hole. Genzel and Gers shared the Nobel Prize in Physics in 2020 for this work. They had proved, as definitively as science can prove anything, that Sagittarius A star is real. And then, in April of 2019, a collaboration of over 300 scientists using a network of radio telescopes spanning the entire Earth, an instrument called the Event Horizon Telescope, captured the first direct image of a black hole. That image showed the supermassive black hole at the centre of a distant galaxy called M87, a monster 6.5 billion times the mass of the Sun. 3 years later, in May of 2022, the same collaboration released something even more personal. The first image of Sagittarius A star, our black hole, the one at the centre of our own galaxy, a blurry, glowing ring of orange and gold light, the shadow of the event horizon against the hot gas swirling around it, sitting at the heart of the Milky Way exactly where the stellar orbit said it should be. It is one of the most remarkable images in the history of science. Not because it is visually spectacular, it is actually quite small and indistinct compared to how dramatic the reality is, but because of what it means to see it. To have, for the first time in the entire history of our species, a photograph of the thing that sits at the centre of our home. Sagittarius A star is, by the standards of supermassive black holes, relatively quiet right now. It accretes gas at a low rate, producing only a modest trickle of energy compared to the blazing active galactic nuclei seen in distant quasars. But quiet is a relative term. It occasionally flares. It occasionally swallows a gas cloud or the disrupted remains of a star and briefly brightens across multiple wavelengths before settling back. It is not dormant, it is waiting. And the evidence we will explore in the chapters ahead suggests that the waiting has not always been this patient. There have been times when Sagittarius A star was not quiet at all, when it was something far more violent, far more luminous, far more terrifying. The monster at the heart of our galaxy has a history, and parts of that history are written in structures so large that they span a significant fraction of the galaxy itself. We are going to read that history together, but first, let yourself sit with this for a moment. The centre of your galaxy has a face now. It is a ring of light around an absolute darkness, and it has been there, patient and immense, for longer than the Earth has existed. There is a group of stars that no human being will ever visit, that no spacecraft we could currently conceive of could ever reach in any meaningful time frame, and yet which we have watched move with our own instruments, tracked across years and decades, mapped in their trajectories with a precision that would have seemed impossible to astronomers of even 50 years ago. These stars orbit so close to Sagittarius A star that their paths take them within distances comparable to the size of our own solar system from a 4 million solar mass black hole. They move so fast that their speeds approach fractions of the speed of light at closest approach. They complete full orbits around the galactic centre, in timescales not of millions of years, as our Sun does, but of decades, some in as little as 16 years. They're called the S-cluster stars, and watching them move is one of the most viscerally affecting things in modern astronomy, because they make the black hole visible in a way that no image ever quite can. They show you the gravity, they let you see it working. The S-cluster is a collection of young, hot, massive stars packed into a region just a fraction of a light year across around Sagittarius A star. That they are young is itself one of the deepest puzzles associated with the galactic centre. These stars are classified as B-type and O-type stars, meaning they are massive, hot, and blue-white, with estimated ages of only a few million years. Here is the problem. The tidal forces from Sagittarius A star at the distances where these stars orbit are so extreme that they should shred apart any gas cloud trying to collapse to form a star. The gravitational gradient across a collapsing cloud at that distance from a 4 million solar mass black hole would tear the cloud apart far faster than gravity could pull it together. By all normal rules of star formation physics, these stars should not exist where they are. They cannot have formed in place, and yet there they are, young and blazing, orbiting a supermassive black hole at distances that should have made their birth impossible. This is known as the paradox of youth, and it is one of several things about the S-cluster that remain genuinely and deeply unexplained. The most famous member of the S-cluster is a star called S2, sometimes written S02 in some classification systems. It is the star whose orbit has been most precisely and most completely measured, and its story is one of the great observational achievements of modern astrophysics. S2 orbits Sagittarius A star on an elliptical path that brings it as close as about 120 astronomical units at its nearest point, and carries it out to about 10 times that distance at its farthest. 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. So at closest approach, S2 passes within about 11 billion miles of a 4 million solar mass black hole. For comparison, Pluto orbits our Sun at an average distance of about 39 astronomical units. S2's closest approach to Sagittarius A star is only about 3 times the distance of Pluto from our Sun, 3 times the distance to Pluto from something 4 million times more massive than the Sun. Think about that for a moment and let it settle into you. At that closest approach, S2 is moving at roughly 2.7% of the speed of light. That is about 18 million miles per hour. No human-made object has ever travelled anywhere near that speed. The fastest spacecraft ever launched, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour at its closest approach to the Sun. S2 moves roughly 40 times faster than that, and it does so not as a brief once-in-a-lifetime event, but as a regular repeating orbital motion. Every 16 years, S2 screams past Sagittarius A star at 18 million miles per hour, and then swings back out on its long elliptical arc, carrying the gravitational memory of that encounter embedded in the precise shape of its path. That path, that precise elliptical orbit, is more than just a spectacle. It is a measurement device of extraordinary sensitivity. By tracking S2's position over multiple complete orbits, astronomers have been able to measure the mass of Sagittarius A star with remarkable precision, confirming 4 million solar masses concentrated in a region smaller than our solar system. They have used its orbit to test Einstein's general theory of relativity in one of the most extreme gravitational environments accessible to observation. And in 2018, when S2 made its closest approach to the black hole, astronomers detected exactly the gravitational redshift predicted by general relativity in its light, the slight reddening of the star's spectrum caused by photons climbing out of such a deep gravitational well that they lose energy in the process. The theory held. The black hole is real, and a single star's dance around it confirmed both facts simultaneously. Beyond S2, the S-cluster contains dozens of other stars on similarly dramatic orbits, each one a slightly different probe of the gravitational geometry around Sagittarius A star, S14, S12, S1, S38, each tracked across years of observation, each contributing a slightly different angle on the same central object. Some of these stars have orbital periods of only a few years, meaning that in the time since their discovery, they have already completed multiple full circuits around a supermassive black hole. The data accumulated from tracking these stars represents one of the most detailed observational portraits of a black hole's gravitational influence ever assembled. It is, in its way, a kind of intimacy. We have watched these stars long enough to know their schedules. There is something that I find quietly haunting about the S-cluster stars, something beyond the physics and the orbital mechanics. These are real stars. They are burning hydrogen in their cores, fusing atoms, generating light and heat. The same fundamental process happening in our own sun right now. Some of them may have planets. We do not know. Given their ages and the extreme environment they inhabit, the odds seem low, but the universe is full of surprises, and we have learned not to be too confident about what it will and will not permit. If there were a planet orbiting one of these stars, its sky would be unlike anything in our experience. The black hole would be visible from its surface not as a visible object, since the black hole itself emits no light, but as a profound and moving darkness, a region of the sky where stars are absent, bent around a gravitational lens, distorted into arcs and rings by the curvature of space itself. And every 16 years or so, the star would make its closest approach, and the tidal forces would flex and strain the planet, and the radiation environment would spike, and the whole system would scream past the most extreme object in the galaxy, and then arc back out into relative calm. Watching the S-cluster stars, I think, is the closest we have yet come to making the abstract reality of a supermassive black hole felt in a human way. Numbers help, images help. But seeing a real star, a burning sun like our own, whipping around an invisible mass at 18 million miles per hour and coming back to do it again 16 years later, that does something different. It makes the black hole present. Tactile in a way that mathematics alone cannot achieve. The S-cluster stars are the black hole's witnesses, the closest things to it that we can observe and track and understand, and they move the way everything near extreme gravity moves. Fast, curved, committed, with no choice in the matter at all. The black hole does not ask, it simply pulls, and everything near enough to feel that pull must dance, whether it wishes to or not. You have almost certainly felt tidal forces in your life, even if you have never called them by that name. If you have ever stood at the edge of the ocean and watched the tide come in, you have seen the result of a tidal force. The moon's gravity pulls on the Earth, but it does not pull on every part of the Earth equally. The side of the Earth facing the moon is slightly closer to it, and so it experiences a slightly stronger gravitational pull than the centre of the Earth does. The side facing away experiences a slightly weaker pull. This difference in gravitational force across the diameter of the Earth, this gradient, is what we call a tidal force. It stretches the Earth very slightly in the direction of the moon and compresses it very slightly in the perpendicular directions. The oceans, being fluid, respond to this stretching and compressing by bulging outward on the side facing the moon and on the opposite side as well, creating the tides. The solid rock of the Earth also deforms by about 30 centimeters or so, though you will never feel it. Tidal forces from a distant moon, acting across a planetary diameter of 12,000 kilometers, produce effects gentle enough to be peaceful and rhythmic. Now imagine those same forces, not from a moon, not across a planetary diameter, but from a 4 million solar mass black hole, acting across the length of a star. The word gentle no longer applies. To understand what tidal forces do near a supermassive black hole, we first need to understand what makes them so devastating at close range. The strength of a tidal force depends on two things: the mass of the object producing the gravity and the distance from it. Specifically, tidal forces scale with the inverse cube of the distance. That means if you halve the distance to a gravitating object, the tidal force does not double, it increases by a factor of 8. Reduce the distance by a factor of 10, and the tidal force increases by a factor of 1,000. This brutal scaling is why tidal forces that are negligible at large distances become catastrophic at small ones. The closer you get to a massive object, the faster the tidal force grows, and it grows in a way that quickly outruns any material strength, any chemical bond, any structural integrity that ordinary matter possesses. Near Sagittarius A star, the tidal forces reach a scale that defies comfortable description. Any extended object, any object with a measurable size rather than being a perfect mathematical point, will experience a differential gravitational pull across its extent when it approaches the black hole closely enough. For a gas cloud drifting inward, this means the near side of the cloud is pulled harder than the far side, and the cloud begins to stretch. First gently, then increasingly violently, the cloud elongates in the direction of the black hole. The stretching accelerates as the cloud falls closer. The near side accelerates faster than the center, and the center faster than the far side, and the cloud begins to look less like a cloud and more like a long, thin stream of gas, reaching toward the black hole on one end, while the other end is still relatively far away. This process has a name that physicists use with complete seriousness, and that sounds almost darkly poetic when you first encounter it. It is called spaghettification. Spaghettification is what happens to any sufficiently large or sufficiently close object that enters the tidal disruption zone around a black hole. The tidal force stretches it in one direction and compresses it in the perpendicular directions simultaneously. The same geometry as the ocean tides, but operating at energies and scales that are absolutely lethal to any structure. A star that wanders too close to Sagittarius A star does not simply fall in. It is first stretched into a long filament of hot gas, wrapped partially around the black hole in a spiraling stream, with roughly half the disrupted material falling inward toward the event horizon, and the other half being flung outward on hyperbolic trajectories back into the surrounding space. The energy released in this process, a tidal disruption event, is enormous. For weeks or months, the galactic center can briefly blaze with the light of hundreds of billions of suns as the infalling stream of stellar material spirals down and heats up in an accretion disk before crossing the event horizon. We have observed these tidal disruption events happening in other galaxies, watched distant galactic centres suddenly flare brilliantly where before there was silence, and we understand what we are seeing. A star dying, being unwound by gravity into a ribbon of plasma, feeding a sleeping monster that briefly wakes to swallow it. The question of what tidal forces would do to a human body near a supermassive black hole is one that people often ask, and the answer is worth sitting with because it illustrates the physics in a viscerally immediate way. Let us say, purely as a thought experiment, that you were falling feet first towards Sagittarius A star from a great distance. Far from the black hole you would feel nothing unusual. The gravity would be pulling you steadily inward, but pulling you uniformly enough that you would feel weightless, the same comfortable freefall feeling that astronauts experience in orbit. But as you fell closer, the difference in gravitational pull between your feet and your head would begin to grow. Your feet, being closer to the black hole, would be pulled harder. The difference would begin as something barely perceptible, then uncomfortable, then painful. Then, at a certain distance from the event horizon, the tidal force across the roughly 2 meters of your body would exceed the tensile strength of every material in you. Bones, muscles, connective tissue, the molecular bonds holding your cells together, all of it would fail simultaneously. You would be stretched rapidly and completely into a very long and very thin stream of particles. The process would be essentially instantaneous by the time it reached that threshold. And here is the detail that makes this thought experiment particularly strange. For a supermassive black hole like Sagittarius A star, that threshold, the point at which spaghettification becomes inevitable and immediate, lies inside the event horizon. You would cross the event horizon while still intact. You would be inside the black hole before the tidal forces became fatal. The universe would be cut off from you. You would be inside a region of no return, and only then would the tidal forces finish their work, invisibly and forever, with no signal of any kind ever reaching the outside universe to confirm what happened. For smaller black holes, stellar mass black holes formed from collapsed stars with masses of 10 or 20 or 30 solar masses, the situation is reversed. The tidal forces at the event horizon of a small black hole are far stronger than at the event horizon of a supermassive one. Because the event horizon is so much smaller and closer to the central singularity, a stellar mass black hole would spaghettify you long before you crossed its event horizon. You would be shredded in open space, visibly, from the outside perspective, before you ever reach the point of no return. In a deeply strange and counterintuitive sense, the most survivable black hole to approach, if survival is even a meaningful concept in this context, would be the largest one. The monster, paradoxically, is gentler at its threshold than the small ones. As we continue our journey and begin to look outward from the galactic centre, the tidal forces we have been contemplating are not merely theoretical curiosities. They are active forces shaping the environment around Sagittarius A star right now. They govern which gas clouds can survive close approach and which are shredded. They influence the orbits of the S-cluster stars, tugging at their structures on every close pass. They set the inner boundary of the region where stable orbits are possible. And they have, over the billions of years of the black hole's existence, processed an enormous quantity of matter through their grinding, stretching, compressing violence. The space near Sagittarius A star is not an empty stage on which the black hole sits passively. It is a region where gravity itself becomes a physical force as real and present as any wind or fire, where the curvature of space is steep enough to tear apart the same kinds of structures that make up you and everything you have ever touched. That is not a comfortable thought, but it is an honest one. And honesty, even when it is a little terrifying, is part of why we are here tonight. In the year 2010, a team of astronomers analysing data from NASA's Fermi Gamma Ray Space Telescope made a discovery that stopped the scientific community in its tracks. They were studying the gamma ray sky, mapping the high-energy radiation coming from different directions across the Milky Way, when they noticed something in the data that should not have been there. Two enormous structures, one above the galactic plane and one below it, glowing in gamma rays with an intensity and a sharpness of boundary that was completely inconsistent with any known diffuse background emission. These structures were not subtle. They were not ambiguous smudges that required careful statistical analysis to tease out of the noise. Once the background was properly subtracted, they were unmistakable. Two colossal bubbles of high-energy plasma, each one extending roughly 25,000 light-years perpendicular to the galactic disk, together spanning 50,000 light-years from tip to tip. They were centered precisely on the galactic center, precisely on Sagittarius A star, and they had been there, hanging above and below the galaxy, completely invisible to any previous survey for the entire history of modern astronomy. We named them the Fermi bubbles, and their existence raises a question whose answer is, in the most literal sense, history-changing. To appreciate the scale of what was discovered, consider this. The Fermi bubbles together span 50,000 light-years. The distance from our Sun to the galactic center is 26,000 light-years. The bubbles extend almost as far above and below the galactic plane as we are from the center horizontally. They are not a local feature. They are not something confined to the immediate neighborhood of the galactic center. They are structures of truly galactic scale, visible features of the Milky Way comparable in size to significant fractions of the galaxy itself. If you could somehow see the Milky Way from outside, from a vantage point above the galactic plane at sufficient distance to take in the whole structure, the Fermi bubbles would be one of the most visually prominent features of the galaxy. Two vast lobes of luminous plasma, like the wings of some incomprehensibly large creature, stretching above and below the galactic disk with their roots planted directly at the galactic center. The immediate question, the one that every astronomer asked the moment the discovery was announced, was, what made them? What event, what process, what release of energy was powerful enough to inflate two structures of this size, to push plasma 50,000 light-years from the galactic plane against the resistance of the galaxy's own gravity? The energy required to create the Fermi bubbles is estimated at around 10 to the power of 55 ergs. That number requires some translation. A single supernova explosion releases about 10 to the power of 44 ergs of energy, most of it in neutrinos. The Fermi bubbles required the energy equivalent of roughly 100 million supernova explosions. That is not a number achievable by any single stellar event or even any single burst of star formation. Something of extraordinary power was involved, and there are, broadly speaking, two candidates. The first candidate is a period of intense, sustained star formation in the galactic center sometime in the past. If the inner galaxy experienced a starburst episode, a period during which an unusually large quantity of gas collapsed into stars in a short time, the resulting supernovae and stellar winds could collectively have driven an outflow of hot gas upward and downward out of the galactic plane. The energy from millions of supernova, detonating over a period of millions of years in a concentrated region of space, could plausibly have inflated structures comparable in scale to the Fermi bubbles. This mechanism is not hypothetical. We observe it happening in other galaxies. Starburst galaxies like M82 show dramatic bipolar outflows, driven by exactly this kind of concentrated stellar activity, hot gas being blown out of the galaxy's disk in opposite directions by the collective energy of an enormous burst of star formation. The galactic center of the Milky Way has the stellar populations and the history to have produced something similar. The second candidate is more dramatic, and it connects directly to Sagittarius A star. A period of active accretion onto the supermassive black hole, a time when Sagittarius A star was not the relatively quiet object it is today, but an active, luminous engine consuming gas at a high rate and driving powerful jets of energy and matter out along its rotation axis, could also have inflated structures of the size and energy of the Fermi bubbles. Supermassive black holes in active galaxies, quasars and Seyfert galaxies are observed to drive exactly these kinds of large-scale outflows. Their jets punch through the surrounding gas and inflate enormous radio-emitting lobes that in some cases dwarf the host galaxy itself. If Sagittarius A star went through a quasar-like phase at some point in its past, even a relatively brief and modest one by quasar standards, it could have produced the Fermi bubbles. The current evidence does not conclusively favour one mechanism over the other. Many researchers suspect both contributed, with the relative importance of each still being worked out through ongoing observations and modelling. What the Fermi bubbles tell us with certainty, regardless of their precise origin, is that the galactic centre has not always been the relatively quiet place we observe today. Something happened. Something big. The bubbles are the scar left by that something, the physical record preserved in the structure of the galaxy's halo of an event or series of events, energetic enough to reshape the environment of the Milky Way on the larger scales. They are a reminder that our galaxy has a history of violence, that the current calm of Sagittarius A star is a relatively recent condition, and that the deep past of our home galaxy included episodes of activity that would have been terrifying on any human scale of reference. The Milky Way wears its scars on the outside if you know what wavelengths to look in. There is also a subtle and somewhat unsettling implication in the Fermi bubbles for the question of life in the galaxy. During the period when whatever created the bubbles was actively operating, the radiation environment throughout a significant volume of the galaxy's halo would have been dramatically elevated. High-energy gamma rays and cosmic rays flooding outward from the galactic center, flowing through the halo, potentially reaching into the disk of the galaxy itself. What effect, if any, this had on life elsewhere in the Milky Way is impossible to say with certainty. We do not know exactly when the bubbles formed. Estimates based on the physics of their expansion suggest somewhere between 1 million and several tens of millions of years ago, though some models push that back further. If the event was recent enough and intense enough, it might have left fingerprints on the biological history of planets throughout the galaxy. It might even have contributed to mass extinction events. We do not know, but the question is not frivolous. As we stand here at the galactic center and look up and down at the structures we have made, at the two enormous bubbles of hot plasma marking the most dramatic event in the recent history of our galaxy, I want you to feel the weight of what they represent. The universe is not static. Galaxies are not permanent, unchanging backdrops. They are dynamic. They have histories. They carry within them the physical record of their most violent moments in the form of structures that persist for millions of years after the events that created them. The Fermi bubbles are not just an astronomical curiosity. They are evidence that the galaxy you live in has been through things. Enormous, energetic, transformative things. And the center of that galaxy, the quiet black hole sitting at the heart of everything, is not innocent of those events. It is, in all probability, their author. There is a concept in astronomy called a light echo, and it is one of the most quietly eerie things in the entire field. When a powerful burst of light or high-energy radiation erupts from a source, it does not only travel outward in a straight line toward distant observers, it also illuminates everything nearby. Clouds of gas and dust in the surrounding region absorb that radiation and then re-emit it, glowing in response to the original flash the way a wall glows when you shine a flashlight at it. The difference is the timescale. Light travels at a fixed speed. If the original burst illuminated a cloud that sits slightly off to the side, the light that hit that cloud has to travel a longer path to reach us than the light that came directly toward us. So we see the echo delayed, sometimes by years, sometimes by centuries, sometimes by thousands of years, depending on the geometry. A light echo is, in effect, a time-delayed photograph of something that already happened. It lets you see the past reflected off the present, and near the galactic center, those echoes are telling us something that should not be ignored. Beginning in the early 2000s, astronomers studying the molecular clouds near Sagittarius A star in X-ray wavelengths noticed something unexpected. Several of the large gas clouds in the central molecular zone were glowing in X-rays, fluorescing in a characteristic way that indicated they were responding to an external source of hard X-ray radiation. This kind of fluorescence, iron atoms in the clouds absorbing X-ray photons and re-emitting them at a specific energy, is well understood and is a reliable indicator of illumination by a powerful X-ray source. The problem was that Sagittarius A star, the obvious candidate for that source, was not, at the time of the observation, producing anywhere near enough X-ray radiation to account for the fluorescence being seen in the clouds. The clouds were responding to something, but the thing they seemed to be responding to had already stopped doing it. What the astronomers were seeing was the echo. The light was still bouncing off the clouds, travelling outward to reach our telescopes, but the original flash that produced it had happened long ago. The calculations that followed were sobering. Working backward from the positions of the fluorescing clouds, their distances from Sagittarius A star, and the geometry of the illumination, astronomers estimated that the original X-ray flare responsible for the echoes had to have originated from the direction of Sagittarius A star somewhere between 100 and 400 years ago. Not millions of years ago, not billions, 100 to 400 years ago. At some point during the period roughly corresponding to the 17th or 18th century in human history, Sagittarius A star produced a burst of X-ray radiation dramatically more powerful than anything it produces today. The estimates of how much more powerful vary between studies, but some analyses suggest the flare was at least 1 million times brighter in X-rays than the current baseline activity of the black hole. For a period that may have lasted decades or perhaps a century or more, Sagittarius A star was not the quiet, sleeping monster we observe today. It was significantly more active, and the echoes of that activity are still washing over the surrounding gas clouds as you lie here, right now, tonight. This is not an isolated finding. Multiple independent lines of evidence point toward a picture of Sagittarius A star that is considerably more dynamic over historical timescales than its current quiescence suggests. There is the Fermi bubbles, those enormous structures requiring an energy input far beyond what the present black hole generates. There are other X-ray reflection features in clouds at varying distances from the centre, each one potentially representing a different episode of past activity, a different flash of awakening at different moments in the black hole's history. And there are theoretical models of how supermassive black holes grow and feed, models that consistently predict that even a relatively low-mass black hole like Sagittarius A star should experience intermittent episodes of elevated accretion, periods when a gas cloud falls into the central region and briefly fuels a significant increase in luminosity before the available fuel is exhausted and the black hole settles back into its resting state. What we observe around Sagittarius A star is entirely consistent with a black hole that wakes up occasionally, feeds for a while, and then goes quiet again. The question is not whether this happens. The evidence that it does is growing steadily. The question is when it will happen next. There is a gas cloud called G2 that provides a somewhat unnerving illustration of how this process works. In 2012, astronomers identified a compact cloud of gas on a trajectory that would bring it very close to Sagittarius A star, with closest approach predicted for 2013. The astronomical community watched with considerable anticipation. Some predictions suggested the cloud would be disrupted by tidal forces as it approached the black hole, with the infalling gas potentially triggering a significant increase in Sagittarius A star's activity. What actually happened was more muted than those dramatic predictions, but illuminating nonetheless. G2 did pass close to the black hole. It was stretched and distorted by tidal forces. Some of its material was disrupted, but the anticipated major flare did not materialize on any dramatic timescale. Sagittarius A star showed some modest increase in flaring activity in the years following the encounter, but remained largely quiescent. The event was a reminder that feeding a supermassive black hole is a complex process, that not every close approach of gas results in a dramatic accretion event, and that the relationship between infalling material and the resulting luminosity involves physics we still do not fully understand on the timescales of individual events. But what the G2 event also demonstrated is that material is continuously approaching the galactic center. The inner galaxy is not a cleared, empty region around a static black hole. It is a dynamic environment where gas, dust, and disrupted stellar material are constantly being channeled inward by the gravitational field of Sagittarius A star and the complex dynamics of the surrounding region. The black hole has a steady, if modest, supply of potential fuel in its immediate environment. Under the right conditions, a larger than usual concentration of infalling gas could trigger a significantly more active accretion episode. The conditions for a more dramatic awakening are not exotic or requiring some unique catastrophic event. They simply require the right quantity of gas arriving in the right way at the right time. The galaxy produces such conditions intermittently, and history tells us that Sagittarius A star has taken advantage of them before. I want to be careful here not to suggest that a catastrophic awakening of Sagittarius A star poses any meaningful threat to Earth or to life on this planet. The galactic center is 26,000 light-years away. Even in its most dramatic known episodes, Sagittarius A star is not a quasar-class object whose radiation could sterilize large fractions of the galaxy. The energy outputs involved, while staggering in absolute terms, are diluted by distance to levels that are inconsequential at our location in the outer galaxy. The terrifying aspect of the black hole's periodic waking is not a threat to us in any practical sense. It is terrifying in a different and more philosophical way. It is terrifying because it tells us that the quiet we observe today is not permanent, that the monster at the center of our home has a history of restlessness, that the Milky Way we live in, the galaxy we call home, is not a static and settled place but a living system with a violent heart that beats on its own schedule, indifferent to our presence, and that will wake again when the conditions are right, as they have been before, as they will inevitably be again. The black hole sleeps, but it has never slept forever. And somewhere in the gas and dust falling slowly inward toward the galactic centre tonight, the seeds of its next awakening may already be in motion. The galactic centre is not only the home of a supermassive black hole, that alone would make it extraordinary, but the black hole is, in a sense, just the most visible resident of a neighbourhood crowded with exotic and dangerous objects, a graveyard of dead and dying stars so densely packed that the volume of space within a few dozen light-years of Sagittarius A star contains more stellar remnants than most regions of the galaxy contain total stars. When massive stars die, they do not simply vanish. They leave something behind. Sometimes a black hole of stellar mass, a few times the mass of the Sun, collapsed into a point of no return. Sometimes something even stranger, a neutron star, an object so extreme in its properties that it exists at the very boundary of what matter is permitted to be, pressing against the limits set by quantum mechanics and nuclear physics simultaneously. A thing that is neither quite a star nor quite something else, but occupies a category so far outside ordinary experience that no analogy fully captures it. The galactic centre is full of them, and they are not all quiet. A neutron star is what remains when a massive star, typically between 8 and 20 times the mass of our Sun, exhausts its nuclear fuel and collapses. The outer layers of the star are expelled in a catastrophic supernova explosion, but the core collapses inward under its own gravity, with a violence that compresses it past the density of an atomic nucleus. The electrons and protons in the core are forced together, combining into neutrons under the extreme pressure, and what remains is a sphere of almost pure neutron matter roughly 20 kilometers in diameter, containing somewhere between 1.5 and 2 times the mass of our Sun. 20 kilometers, the distance you might drive to reach a neighbouring town. Compressed into that sphere is more mass than our entire Sun. The density of a neutron star is so extreme that a single teaspoon of its material would weigh roughly 4 billion tons on Earth. It is the densest form of matter known to exist in the observable universe, stopping just short of becoming a black hole by virtue of quantum mechanical pressure that prevents the neutrons from being compressed any further. At least, that is the current understanding. The interior physics of neutron stars involves conditions so extreme that our equations become uncertain, and our models begin to disagree with one another. Neutron stars come in several varieties, and the galactic centre hosts representatives of the most extreme among them. Ordinary neutron stars spin rapidly and emit beams of radio waves from their magnetic poles, sweeping those beams across space like cosmic lighthouses. When those beams happen to sweep past the Earth, we detect them as precisely timed pulses of radio emission, and we call the sources pulsars. The timing of pulsar pulses is so regular, so extraordinarily precise, that the first ones discovered were briefly and seriously considered as possible signals from an intelligent civilization. They are in fact among the most accurate natural clocks in the universe, rivaling atomic clocks in their precision over short timescales. Several pulsars have been discovered in and near the galactic centre, and studying them there is scientifically valuable precisely because their precise timing signals can be used to probe the gravitational field of Sagittarius A star in ways that complement and extend what we learn from stellar orbits. But there is a subclass of neutron star that takes everything already extreme about these objects and amplifies it into something that belongs in a different category of dangerous entirely. Magnetars are neutron stars with magnetic fields so powerful that they dwarf even the already formidable fields of ordinary pulsars by factors of hundreds or thousands. The magnetic field of a typical magnetar is roughly 1 quadrillion times stronger than Earth's own magnetic field. At a distance of roughly 1,000 kilometers from a magnetar, the magnetic field would be strong enough to disrupt the quantum mechanical structure of atoms themselves, pulling the electron clouds of atoms into elongated shapes aligned with the field and fundamentally altering the chemistry of any matter that found itself that close. There is a magnetar near the galactic centre, designated SGR J1745-2900, sitting within just a few light-years of Sagittarius A star. It is one of the closest known magnetars to our position in the galaxy. Periodically, it emits bursts of X-rays and gamma rays powerful enough to be detected clearly by our satellites from 26,000 light-years away. A brief pulse of energy, crossing that incomprehensible distance, arriving at our instruments still strong enough to register clearly. What that pulse feels like at the source is something that does not bear comfortable contemplation. Beyond individual neutron stars and magnetars, the galactic centre is home to a population of X-ray binary systems, pairs of stars in which one member is a compact object, either a neutron star or a stellar mass black hole, actively feeding on material from its companion. In an X-ray binary, the compact object's gravity pulls gas from the outer layers of the companion star, stripping it away in a steady stream. That gas spirals inward in a disk, heating to temperatures of millions of degrees as it falls, and radiates prolifically in X-rays before crossing the event horizon, or colliding with the neutron star surface. The galactic centre region hosts an unusually high concentration of these systems. Surveys with X-ray telescopes have revealed hundreds of X-ray point sources within the central few dozen light-years, many of them consistent with X-ray binaries in various states of activity. The stellar crowding of the inner galaxy, combined with the long history of star formation and stellar evolution in the region, has had billions of years to produce and concentrate these exotic pairing systems through gravitational interactions and stellar evolution. There is also the question of stellar mass black holes. Every massive star that has ever lived and died in the galactic centre region has left behind either a neutron star or a black hole. The galactic centre has been forming stars for over 10 billion years, with the inner regions hosting some of the highest rates of massive star formation anywhere in the galaxy. The number of stellar mass black holes that have accumulated in the inner parsec, the region within a few light-years of Sagittarius A star over that entire history, is estimated in the thousands, possibly tens of thousands. Most of them are invisible in isolation, black holes drifting silently on their orbits, detectable only when they happen to be in a binary system where they are actively accreting. But they are there. A dark, dense population of stellar corpses orbiting the supermassive black hole, each one a gravitational hazard to anything that passes too close, each one the remnant of a star that lived, burned and died in one of the most extreme environments our galaxy contains. What all of this amounts to, as you let it settle over you in the dark, is a portrait of the galactic centre as something genuinely unlike any other region of the Milky Way accessible to our study. It is not merely extreme in one dimension, it is extreme in every dimension simultaneously. Extreme stellar density, extreme radiation environment, extreme gravitational dynamics, extreme concentrations of exotic objects, neutron stars, magnetars, X-ray binaries, stellar mass black holes, all orbiting the supermassive black hole that anchors the entire system, all embedded in gas heated to millions of degrees, all bathed in radiation levels that would be immediately lethal to any unshielded biology. The galactic centre is the most spectacular and most dangerous place in the Milky Way, not because of any single feature, but because of the combination of all of them operating together, layered on top of one another in a volume of space that, relative to the full size of the galaxy, is almost infinitesimally small. It is a compressed archive of extremity, a place where the universe demonstrates without restraint or apology just how far it is willing to go. One of the questions I find myself returning to, again and again, when I think about the galactic centre is a very simple one. Could anything live here? Not survive in the sense of a rock surviving, persisting passively through billions of years of bombardment without chemistry or complexity or awareness, but live in the biological sense. Could there be planets near the galactic centre? Could those planets have surfaces liquid enough, stable enough, shielded enough to host the slow and patient chemistry that eventually, over billions of years, produces something that breathes and moves and wonders? It is a question that feels almost absurd to ask after everything we have explored together tonight. And yet it is worth asking seriously, because the answer is not as simple as the environment might suggest, and because the way we answer it says something important about what life requires and where in the universe it might be found. Let us start with the most immediate and obvious challenge: radiation. The galactic centre is bathed in radiation at levels that dwarf anything experienced in the outer galaxy where Earth resides. X-rays from accreting compact objects and hot plasma, gamma rays from cosmic ray interactions and from the activity of Sagittarius A star, ultraviolet radiation from the enormous population of massive hot stars in the arches and quintuplet clusters and throughout the inner galaxy. Cosmic rays, high-energy particles accelerated to near light speed by shock waves and magnetic fields, flooding the central molecular zone at densities roughly 1,000 times higher than what we experience near the Sun. On Earth, the atmosphere and the planet's magnetic field together provide substantial shielding against most of these radiation types. Life on Earth's surface is protected by layers of air, equivalent in shielding to several meters of water, but even with all of that protection, high-energy cosmic rays and solar energetic particles still reach the surface and contribute to the mutation rate in biological organisms. A planet in the inner galaxy, even one with a substantial atmosphere and magnetic field, would face a radiation environment severe enough to significantly accelerate mutation rates and potentially overwhelm the DNA repair mechanisms that life on Earth relies on. Then there is the question of gravitational stability. In the outer galaxy, planetary systems can persist for billions of years in relative isolation. The Sun's nearest stellar neighbour is 4 light-years away, and in the 4.5 billion years of the solar system's existence, no passing star has come close enough to significantly disrupt the orbits of the major planets. That stability is what allowed Earth to maintain liquid water on its surface for long enough for complex life to evolve. It took roughly 4 billion years from the first appearance of life on Earth to the emergence of multicellular organisms. In the inner galaxy, where stars are separated by fractions of a light-year and where the stellar population is constantly churning on the faster orbital timescales near the galactic centre, close stellar encounters are far more frequent. A planetary system in the inner galaxy might have its outermost planets stripped away by a passing star. Its remaining planets might have their orbits perturbed into elongated ellipses that carry them alternately too close to and too far from their host star for liquid water to persist. The long-term orbital stability that Earth has enjoyed is a much rarer commodity near the galactic centre. And yet, here is the thing most people do not realise when they think about habitability near the galactic centre. The challenges are real and severe, but they are not uniformly distributed, and they are not absolute. The inner galaxy is not a single undifferentiated zone of doom. It has structure. It has regions of higher and lower radiation density. It has stars that, despite their proximity to more massive and more luminous neighbours, might still host planets in relatively stable orbits on timescales of hundreds of millions of years. Not the billions of years that Earth required, perhaps, but enough time for simple life to emerge and potentially even for evolution to do some of its work. Simple microbial life on Earth appeared quite quickly by geological standards, within the first billion years of the planet's formation, possibly within the first few 100 million years. If life can appear that quickly, given reasonable conditions, then even a planet with a shorter window of stability than Earth might not be ruled out entirely. There is also the question of what life requires at the chemical level. One of the prerequisites for life as we know it is the availability of heavy elements: carbon, nitrogen, oxygen, phosphorus, sulfur, iron, and several others. These elements are produced inside stars by nuclear fusion and distributed into the interstellar medium by stellar winds and supernova explosions. The inner galaxy, with its long history of intense star formation and the deaths of enormous numbers of massive stars, is actually chemically richer in many of these heavy elements than the outer galaxy. The gas in the central molecular zone, as we explored earlier, contains complex organic molecules in quantities that dwarf anything found in the quieter outer spiral arms. In terms of raw chemical ingredients, the galactic centre is not impoverished. If anything, it is lavishly supplied with the building blocks that life uses. The problem is not the ingredients. The problem is the energy environment that keeps disrupting any attempt by those ingredients to organise into stable, self-replicating structures. Astronomers have developed a concept called the galactic habitable zone, analogous to the more familiar stellar habitable zone around individual stars. Just as there is a range of distances from a star where liquid water can persist on a planet's surface, there appears to be a range of distances from the galactic centre where the conditions for complex life are most favourable. The inner boundary of the galactic habitable zone is thought to lie somewhere between several thousand and perhaps 10,000 light-years from the galactic centre, though different models place it differently. Interior to that boundary, the radiation environment and dynamical instabilities become severe enough to significantly reduce the probability of complex life arising and persisting. Our own Sun sits comfortably within the galactic habitable zone, at a distance of 26,000 light-years from the centre, and the 4.5 billion years of orbital stability and moderate radiation environment we have enjoyed are very much a product of that favourable address. But I want to resist the temptation to draw the galactic habitable zone too cleanly, because the universe has a long history of confounding our expectations about where life can and cannot exist. Life on Earth has been found in hydrothermal vents miles below the ocean surface, where sunlight never penetrates. It has been found in highly acidic hot springs, in highly alkaline soda lakes, in the frozen dry valleys of Antarctica, in rocks kilometres below the surface of the Earth, in places where the temperature, the chemistry, the pressure, and the radiation environment would kill an unprotected human instantly. We call these organisms extremophiles, and their existence is a constant reminder that life, once it gets started, is remarkably tenacious and remarkably creative about finding ways to persist in conditions that seem hostile from the outside. If life exists near the galactic centre, it may be doing something we have not thought of. Using the abundant energy of the radiation environment rather than hiding from it. Sheltering in subsurface oceans on planets whose surfaces are sterilized but whose interiors are geologically warm and chemically rich. Finding niches we have not imagined because we have only ever studied life in one place. We do not know if anything lives near the galactic centre. The honest answer to the question this chapter asks is probably not complex life as we know it, but possibly microbial life in shielded environments, and we cannot be certain of even that. What the question does, beyond whatever answer we might eventually reach, is remind us that the boundary between the habitable and the uninhabitable is not a sharp line. It is a gradient, a probabilistic spectrum, shaped by factors we are still working to understand. The galactic centre challenges every simple model of habitability we have tried to build, and in that challenge, as in everything else about this extraordinary place, it is teaching us something, not just about the galactic centre, about what life is, what it needs, and how much of the universe might quietly, in ways we have not yet learned to recognise, be full of it. We have been travelling inward for the entire duration of tonight's journey, inward through the interstellar medium, through the crowded inner galaxy, through the central molecular zone, past the monster star clusters and the magnetic filaments and the plasma lobes, all the way to the supermassive black hole at the heart of our galaxy and the extraordinary environment surrounding it. But now I want to do something different. I want to turn around. I want to stand here at the galactic centre, in imagination, in the quiet of wherever you are, and look outward. Look back the way we came. Look toward the outer galaxy, toward the Orion Arm, toward the modest yellow star that sits there among hundreds of billions of others, and try to find, across 26,000 light-years of space, something that matters to you. I want us to try, together, to see the Earth from here. The first thing you notice when you turn to face the outer galaxy from the galactic centre is the sheer number of stars between you and your destination. You're not looking through empty space. You're looking through the full disk of the Milky Way, through its spiral arms and its molecular clouds and its stellar nurseries, through tens of thousands of light-years of gas and dust and burning suns. The density of stars around you, in the inner galaxy, means that every direction you look is populated with blazing neighbours, the permanently twilight sky we explored in Chapter 4 still filling every corner of your field of view. But as your gaze travels outward, past the inner few thousand light-years, the stellar density begins to drop. The sky begins, gradually, to thin. The glow becomes less overwhelming, and somewhere out there, roughly in the direction of a particular sparse region of a minor spiral arm, invisible against the background blaze of 200 billion other stars, is a single yellow dwarf of entirely average properties. The Sun. You cannot see it. That is the first thing to accept. From the galactic centre, our Sun is utterly indistinguishable from the billions of other stars scattered across the disk of the galaxy. It is not particularly bright. It is not particularly large. It is not located in any especially prominent or easily identified region of the sky, as seen from the centre. If you had never been told it existed, if you had no prior knowledge of its location, you would have no way of finding it. It is one among hundreds of billions, lost in the crowd with no distinguishing features visible at this distance. The star that is, from our perspective, the centre and source of all warmth and light and life, the gravitational anchor of our entire solar system, the object that dominates our sky and drives our seasons and has been worshipped under 1,000 different names by every civilization our species has ever built, is, from the galactic centre, nothing. A data point, a number in a catalogue that does not yet exist, invisible. And the Earth, from this distance, is not even that. The Earth is roughly 150 million kilometres from the Sun, 1 astronomical unit. From the galactic centre, 26,000 light-years away, the angular separation between the Earth and the Sun is so vanishingly small that no instrument we have or could realistically conceive of building would be able to resolve them as separate objects. They blend together into a single point of light, and that point of light blends into the general glow of the Orion Arm's stellar population, and the Orion Arm blends into the broader disk of the galaxy. Everything you have ever known, every place you have ever been, every person you have ever loved, every sunset you have ever watched, every conversation you have ever had, every moment of joy and grief and wonder and boredom that has ever made up a human life is contained within a region of space so microscopically small by galactic standards that it is simply not visible from here, not hidden by intervening dust, not too faint to detect with better instruments, genuinely, physically impossible to distinguish from everything around it at this scale. The pale blue dot that Carl Sagan described, photographed by Voyager 1 from only 6 billion kilometres away, was already heartbreakingly small. From the galactic centre, that dot, along with the Sun and the entire solar system, has ceased to exist as a separate object at all. There is a particular flavour of vertigo that comes with truly sitting with this perspective, and I do not want to rush past it. I want you to feel it slowly and without alarm as something that is simultaneously terrifying and clarifying. Every war ever fought on Earth was fought over a fraction of that invisible point. Every border, every nation, every empire that has ever risen and fallen did so within a region of space that, from 26,000 light-years away, is smaller than the smallest unit of measurement our eyes can detect. The conflicts that feel world-defining, the anxieties that fill the ordinary days of human life with weight and urgency, the differences between people that have historically seemed important enough to kill and die over. From here, they do not merely seem small. They are physically contained within something invisible. The scale does not diminish them exactly, because human experience has its own scale and its own validity. But it does place them, it puts them in context, and that context is, I find, more peaceful than it is distressing once you let yourself settle into it. At the same time, there is something extraordinary about the fact that the invisible point out there, the one you cannot find and could not identify, even with the best instruments imaginable from this vantage point, is the place where something unique has happened. Life, awareness, the capacity to look outward, to build instruments, to gather light from distant stars and decode from it the structure of the galaxy those stars inhabit. No other point in the galaxy, as far as we know with any evidence, has yet produced anything capable of asking the question we're asking tonight. No other speck in the disk of 200 billion stars has yet generated a mind capable of standing, in imagination, at the galactic centre and looking back. That does not make our speck special in any cosmic sense. The universe did not arrange itself to produce us, and our presence here is the result of an immeasurably long chain of physical and chemical and biological events that had no awareness of where they were heading. But it does mean something, in a quiet and personal way, that the galactic centre we are contemplating is being contemplated. That the universe, here in this specific invisible location, 26,000 light-years from its own heart, has folded back on itself in a way that permits reflection. Looking back from the galactic centre also gives us a new way to understand the journey we've taken tonight. We travelled inward through increasing extremity, through environments that become progressively more violent and more alien with every step toward the centre. And now, looking back along that path, we can see the gradient in reverse. The outer galaxy, where we started, is gentle by comparison to everything we have passed through. It is not perfectly safe, the universe never is, but it is calm enough, stable enough, radiation quiet enough, that a small rocky planet can hold liquid water on its surface for 4.5 billion years, that a yellow dwarf star can burn steadily for that same duration without catastrophic variation, that an unbroken chain of chemical reactions can proceed, generation after generation, elaborating slowly into something as improbable and as precious as a living, thinking creature lying in the dark, listening to the story of where its atoms came from. The outer galaxy did not have to be this way. It is this way because the galactic centre, with all its violence, processed material through stellar generations and distributed it outward across the disk, and the disk settled into regions of relative calm at the right distances from the chaos at the heart. We are calm water downstream from a turbulent source, and the turbulence upstream is what made us possible. We have travelled a long way tonight, from the quiet outer galaxy where our sun burns alone in its local darkness, through the vast and varied interstellar medium, past the blazing inner galaxy where stars crowd together in permanent twilight, through the turbulent central molecular zone with its warm gas and impossible magnetic threads, past the monster star clusters burning at the theoretical limits of stellar physics, through the radio lobes and the ancient plasma scars, all the way to the heart of it all, to Sagittarius A star and the extraordinary, violent, beautiful environment that surrounds it. We looked at the stars that dance with death. We felt the tidal forces that rip matter into streams. We read the scars the Fermi bubbles wrote across the face of the galaxy. We looked back from the centre and could not find our home. And now, at the end of this long and quiet journey, I want to sit with you for a moment in the dark and think about what it means. Not the physics of it, not the numbers, what it means personally, intimately, for the small and temporary creatures that we are. Every atom of carbon in your body was forged inside a star. That is not a metaphor. It is not a poetic approximation of the truth. It is the precise, literal, physical reality of how carbon comes to exist in the universe. The Big Bang produced hydrogen and helium and small traces of lithium. Everything heavier than that, every element in the periodic table beyond those three, was produced inside a star or in the violent death of a star. The carbon that forms the backbone of every organic molecule in your cells was fused from helium nuclei in the cores of stars that lived and died before the sun was born. The oxygen you breathe was produced in similar fashion. The iron in your blood was forged in the final moments of a massive star's life, synthesized in the last heartbeats before a supernova explosion scattered it across light years of space. The calcium in your bones, the phosphorus in your DNA, the nitrogen in the proteins that make every metabolic process in your body possible. All of it, every element that makes you chemically what you are, was cooked in a stellar interior and then released into the galaxy by stellar death. Now here is the part that connects directly to the journey we have taken tonight. The stars that made your atoms didn't all form where the sun formed. Many of them were born in the inner galaxy, in regions far closer to the galactic centre than our current address. The Milky Way has been forming stars for over 13 billion years, and the material cycling through those stars has been distributed across the galaxy over that entire time, moved outward by supernova explosions and stellar winds, mixed by the turbulent dynamics of the interstellar medium, carried from the dense inner regions toward the calmer outer disk on timescales of hundreds of millions to billions of years. Some of the carbon in your body may have spent time in the stars that orbited the galactic centre, at distances far smaller than the Sun's current orbit. Some of it may have been processed through the turbulent gas of the central molecular zone. Some fraction of you, in a very real physical sense, has already been to the place we have been exploring tonight. The journey was not new, it was a return. I find that thought almost unbearably moving when I let myself sit with it fully. The galactic centre is not a foreign and alien place that exists separately from you. It is, in a deep material sense, part of your history. The monster at the heart of our galaxy, Sagittarius A star, has been organising the motion of stars in the inner galaxy for billions of years, and the stars whose explosions seeded the galaxy with the elements of life were influenced in their formation and their motion by that same gravitational anchor. You're connected to the galactic centre, not by proximity or by direct experience, but by the long, branching, patient chain of physical causality that runs from the formation of the galaxy itself, through the births and deaths of billions of stars, through the dispersal of their material, through the slow condensation of that material into the solar nebula, through the formation of the Earth, through the emergence of life, through 4 billion years of biological evolution, all the way to the specific, unrepeatable arrangement of atoms that is you, lying here in the dark, listening to a story about where you come from. That chain is real. Every link in it is physical, and the galactic centre sits near the beginning of it, one of the ancient engines that set everything else in motion. The universe is 13.8 billion years old. Our galaxy is only slightly younger, roughly 13.5 billion years of stars forming and dying and scattering their material and new stars forming from that scattered material in an ongoing cycle that has never fully stopped. The Sun is 4.6 billion years old, a second or third generation star formed from material that was already ancient when the solar nebula began to collapse. Life on Earth appeared within the first billion years of the planet's existence and has been elaborating on that first appearance ever since, through all the mass extinctions and all the evolutionary experiments and all the contingent accidents of biology that eventually, recently, produced nervous systems complex enough to form abstract thoughts. The timeline from the galactic center's formation to you is so long and so intricate that it feels almost impossible that it arrived at anything as specific and improbable as a conscious mind. And yet here you are, here we are, aware in the dark of the size of the thing we are part of. There is a phrase that I return to often when I think about all of this. We are the universe noticing itself. It sounds simple, almost too simple, like something that could be dismissed as pleasant but vague. But I think it is actually one of the most precise and most important things that can be said about the human condition when viewed from a cosmic perspective. The universe, for most of its 13.8 billion years, has not been aware of itself. It has been matter and energy operating according to physical laws, producing structures of extraordinary complexity and beauty, but doing so without any observation, without any witness, without any mind to hold a model of what is happening and feel something in response to it. And then, in the last blink of cosmic time, in a tiny and unremarkable corner of an ordinary spiral galaxy, some of that matter organized itself in such a way that it became capable of looking outward and saying, "I am here, and it is vast, and I feel something about that. That is what you are. That is what we're doing tonight." So as we come to the end of our journey, as we begin to settle back from the galactic center toward the quiet outer galaxy that is our home, I want to offer you something to carry with you into sleep. The galactic center is violent and extreme and in many ways terrifying. We have not shied away from that tonight. The tidal forces, the radiation, the sleeping monster and its history of waking, the graveyard of stellar corpses, the plasma scars written across the face of the galaxy, all of it is real, and all of it is ongoing. But none of it makes the universe hostile to us in any personal sense. The universe is not hostile. It is simply vast, and it operates on timescales and at energies that make human concerns seem small by comparison. That smallness is not a tragedy. It is a context. And within that context, the fact that matter arranged itself here at this specific address in the outer arm of an ordinary galaxy in such a way as to produce something capable of understanding its own cosmic origin is not small at all. It is, by any honest accounting, the most remarkable thing we know of in the observable universe. Thank you for joining me tonight. Thank you for making this journey all the way from the quiet darkness of home to the blazing, turbulent, extraordinary heart of our galaxy and back again. If tonight left you with a sense of wonder that you want to carry further, please take a moment to like this and subscribe. It is a small thing, but it helps this channel continue doing exactly this, sitting together in the dark, exploring the size and strangeness of the place we live. The next time you step outside on a clear night and look up toward the southern sky, toward that dense and luminous band of light that is the Milky Way, know that you are looking toward the center of the structure you have always lived inside. Know that 26,000 light-years in that direction, a 4 million solar mass black hole is quietly waiting, surrounded by its graveyard of dead stars and its ancient plasma scars, patient and immense, older than the Earth by billions of years. And know that some of the atoms inside you have already been there. You're made of the galaxy's long history. You're the heart looking at itself from a safe distance. Sleep well tonight, and keep looking up at the stars.